Hello everyone, and welcome to Earth Archives. Have you ever wondered that every atom in your body comes from stars that died billions of years ago? This isn't poetry, it's a scientific miracle. From the Big Bang to stellar nucleosynthesis, and then to supernova explosions and neutron star collisions, the birth, evolution, and shaping of the elements that make up our world is a magnificent story spanning tens of billions of years. In this video, we'll journey through the river of time together, tracing the creation of elements, from hydrogen and helium to gold and uranium, revealing how the universe built the foundation for life and civilization. If you're curious about astronomy, physics, stellar evolution, and the cosmic periodic table of elements, you absolutely can't miss today's episode. Subscribe to our channel now and turn on the notification bell so you won't miss any of our knowledge feasts. Also, please share your thoughts on the origin of the universe's elements in the comments. Every comment and share is our greatest motivation to keep creating. Amid the vast expanse of cosmic history, every speck of dust, every drop of water, and even every atom in our bodies carries a legendary story born from the stars. Yes, we are all descendants of stardust. The air you breathe, the ground beneath your feet, and even the phone in your hand were forged through a series of intense and spectacular astronomical events in the universe. And it all begins with the Big Bang 13.8 billion years ago. The birth of the universe was no accident. It was a profoundly long and intricate process of evolution. Imagine, at first, the matter in the universe was like scattered dust particles drifting in the boundless void, without order, without form. Yet, gravity, this mysterious force, quietly began to take effect, like an invisible master gently drawing these tiny particles together. At the same time, electromagnetic forces subtly influenced the attraction and repulsion among charged particles, allowing these fundamental materials to combine and form increasingly complex structures. Over time, these combined particles gradually evolved into various celestial bodies, from the earliest small nebulae to massive stars and galaxies. At the heart of all this change lies the birth and evolution of elements, the universe's most basic building blocks. These elements are continuously forged and transformed within the fiery furnaces of stars, driving the ongoing development of the cosmos. The evolution of stars is the grand stage where elements undergo transformation. Starting with the fusion of hydrogen nuclei, stars continuously fuse heavier elements within their cores, helium, carbon, oxygen, up to iron. This journey is far from simple. Each step is a miracle of extreme heat and pressure. When a star's fuel burns down to iron, a crucial turning point arrives. Iron fusion no longer releases energy, but instead consumes it, disrupting the delicate balance within the star and triggering a cataclysmic explosion, a supernova. In the vast expanse of the universe, hydrogen is the most abundant and fundamental element, like the universe's raw material warehouse. Through telescopes and various scientific instruments, we've found that hydrogen makes up the overwhelming majority of elements in the cosmos, present everywhere, from interstellar gas and nebulae to stars themselves. This makes perfect sense, as hydrogen sits at the very top of the periodic table, the starting point and cornerstone of all elements. Speaking of the periodic table, we must mention the great contribution of Russian chemist Dmitry Mendeleev in 1869. At that time, he arranged the 66 known elements according to atomic weight and properties, successfully predicting the existence and characteristics of elements yet to be discovered. This table became the foundational map of chemistry and physics, laying a solid groundwork for future research on elements. With advances in science and technology, modern scientists have identified as many as 118 elements, 92 of which occur naturally on Earth and in the universe, while the remaining 26 have been created artificially through laboratory synthesis. These naturally occurring elements make up everything in our daily lives, from the oxygen we breathe to the silicon in the ground beneath us, to the carbon and iron in our bodies, all intricately tied to these fundamental building blocks. Although the artificially synthesized elements exist only briefly and are highly unstable, they have deepened our understanding of the basic structure of matter and have driven advancements at the forefront of nuclear physics and material science. Among this vast family of elements, uranium, element number 92, is undoubtedly the heaviest element found naturally on Earth. It is like the heavyweight champion of our planet, possessing a massive atomic nucleus and abundant nuclear energy. Although uranium is rare in nature, it plays a crucial role, especially in nuclear power generation and nuclear weapons. However, when we talk about elements heavier than uranium, things become even more fascinating and complex. These elements with atomic numbers exceeding 92 are collectively known as superheavy elements. They do not naturally occur on Earth, but must be artificially synthesized in laboratories using cutting-edge technology. The nuclear structures of these superheavy elements are extremely large and unstable, giving them very short lifespans, from a few milliseconds to a few seconds, sometimes even less, almost a born-to-die fate. This is why they are almost impossible to find in natural environments. Scientists have employed a variety of advanced equipment and techniques to uncover the secrets of these superheavy elements. These include using high-energy neutron bombardment, the extreme conditions produced by nuclear explosions, and the most cutting-edge heavy-ion accelerators today. These devices can collide atomic nuclei at extremely high speeds, allowing them to briefly fuse together and create new superheavy elements. This process is both like an intense particle dance and a spectacular cosmic event where new elements are explosively born. For example, in 2014, Japan successfully synthesized element 113 using an accelerator. This achievement not only pushed the boundaries of the periodic table, but also demonstrated humanity's limitless potential in exploring the microscopic world. Although these superheavy elements have extremely short lifespans, their existence reveals the limits of atomic nucleus structure and drives progress in physics, chemistry, and even cosmology. Indeed, the formation of elements in the universe is like a long and magnificent interstellar story, with stars undoubtedly playing the leading roles. After the Big Bang, as the universe gradually cooled, only the simplest light elements, hydrogen and helium, existed at first. These elements served as the foundation of the cosmos, laying the groundwork for everything that followed. As time passed, hydrogen and helium gradually began to gather under the pull of gravity, forming the very first stars. Inside these stars, temperatures and pressures soared to astonishing levels, millions, even billions of degrees. These extreme conditions acted like cosmic furnaces, forging heavier and heavier elements. Nuclear fusion reactions within the stars fused lighter elements layer by layer into heavier ones, starting from hydrogen fusing into helium, then carbon, oxygen, silicon, and eventually iron. In a sense, stars are not only the shining lights of the universe, but also elemental factories. A star's lifespan and mass determine how many different elements it can produce, and how these elements are dispersed back into the cosmos. When a star massive enough reaches the end of its life, it explodes as a supernova, a magnificent cosmic fireworks display that scatters heavy elements across interstellar space, providing the raw materials for future planets and life. The nuclear fusion within stars truly acts as the universe's master chef, gradually cooking simple elements into increasingly complex, heavy elements. The burning of hydrogen into helium is an energy-producing process, like a flame that continuously supplies light and heat to the star. Once hydrogen is depleted, the star changes its menu and begins fusing helium, then synthesizing carbon, oxygen, neon, and other elements, a process akin to a carefully orchestrated chemical transformation show. The appearance of iron, 56, is like the chef telling us, "I've cooked to perfection." Iron, 56, has the highest nuclear binding energy, meaning that to fuse heavier elements beyond it, a star must absorb energy rather than release it. This creates an energy barrier that stars cannot overcome. This is why nuclear fusion inside stars can only continue up to iron. To produce elements heavier than iron, stars must rely on other extreme events, such as supernova explosions or neutron-star mergers. These violent cosmic explosion parties provide enough energy and neutrons to drive the formation of heavier elements. Iron acts like an energy peak in the universe. Crossing it requires a tremendous cost, but it also gives birth to the most fascinating world of heavy elements. Among all elements, iron 56 has the greatest binding energy, which is crucial because it marks the end point of the fusion process. Why is this the case? Let's start by looking into the microscopic world of particles. All matter is made up of atoms, and atoms themselves consist of a nucleus surrounded by electrons. The atomic nucleus is very special, not a simple sphere, but a tightly bound cluster of two fundamental particles, protons and neutrons. Protons carry a positive electric charge, much like tiny magnets that repel each other. Neutrons, on the other hand, are neutral and carry no charge but act as mediators. Through the strong nuclear force, they bind protons and neutrons tightly together. This strong nuclear force is like an incredibly powerful glue that overcomes the electromagnetic repulsion between protons, keeping the atomic nucleus stable. The binding energy is the energy released when these particles are glued together, and it also represents the energy required to break apart the nucleus. When we try to separate nucleons, that is, the protons and neutrons within the atomic nucleus, we must overcome their strong binding force. This energy is called the binding energy. The greater the binding energy, the more stable the nucleus is. Dismantling or altering its structure requires more energy. Among all elements, iron 56 has the highest binding energy, making it an extremely stable element, neither easily split nor readily fused with other elements. In other words, elements lighter than iron 56 in the universe, like hydrogen, helium, and carbon, gradually fuse into heavier elements through nuclear fusion, ultimately moving toward iron 56. Conversely, elements heavier than iron 56 tend to be unstable and slowly decay, or revert back to the relatively stable state of iron 56 through various radioactive decays and nuclear reactions. It's like an energy mountain peak in the world of elements, with iron 56 standing at the summit, attracting elements on both sides, whether by fusion or decay, to this stable point. This also explains why the nuclear fusion process in stars abruptly stops when forming iron. Nuclear fusion inside stars typically releases a tremendous amount of energy, sustaining their brightness and heat. However, when fusion reaches iron 56, the energy required to fuse iron into heavier elements far exceeds the energy released, making the process energetically unfavorable. In theory, fusion of iron isn't impossible, but it demands extremely harsh conditions and a massive energy input, conditions nearly impossible to achieve naturally inside a star. That's why fusion in stars halts at iron 56, and afterward, stars enter their final life stage, such as a supernova explosion. These dramatic cosmic events then become the birthplace of elements heavier than iron. Although nuclear fusion stops at iron 56 inside stars, heavier elements do not simply appear out of nowhere in the universe. Their creation depends entirely on some of the most violent and extreme astronomical phenomena, especially supernova explosions and neutron-star collisions. Imagine a massive star nearing the end of its life, its core running out of fuel and unable to support its own weight. It begins to rapidly collapse, triggering a powerful supernova explosion. The energy released in this explosion is so immense that it instantly blasts the star's outer layers into space while creating extremely high temperatures and pressures, virtually the most violent cosmic furnace in the universe. In such an environment, the interior of the star is flooded with a huge number of high-speed neutrons. These neutrons are continuously captured by surrounding atomic nuclei, causing the nuclei to rapidly absorb neutrons